In this lecture, we're going to look at drawing molecular orbital diagrams of pi systems. So let's go ahead and get that down. So here, what we're looking at is the arrangement of anti-bonding, bonding, anti-bonding, and non-bonding molecular orbitals for pi bonds only. So pi bonds only. Okay. So what we do is start with a simple case of ethene. Start with ethene, which is CH2, double bonded to CH2. So in this case, we have a bunch of bonds. We have a bunch of elements now compared to H2 and He2, but we have one pi bond, and that's all we're focusing on. The second bond in our double bond, the pi bond. Okay, so we have one pi bond. Within that one pi bond, we then have two pi electrons. In many cases, the number of pi bonds is going to tell us how many pi electrons that we have. Okay. These two pi electrons are shared via the pi bond across the two C atoms. Okay, so that's going to tell us the number and types of orbitals that we have. Sorry, I just need to create a few pages. Sorry, there we go. So it's going to tell us the number of electrons that we have to consider, and it also gives us a hint as to the number of atomic orbitals that we have to use. So the atomic orbitals are non-hybridized p orbitals. Non-hybridized p orbitals. That's really important for recognizing this. I can't emphasize this enough. We're basically ignoring all the sigma bonds, and we just want to talk about the pi bonds because we want to get into pi systems, extended pi systems, which are a key feature of resonance structures and conjugated pi systems. Okay, so we have two electrons, two atoms, two p orbitals that come together to form a molecular orbital. Okay, so now we can build our molecular orbital energy diagram. It's going to look like this. These are going to be our atomic orbitals that come together in the middle to make our molecular orbitals, a high antibonding orbital and a low bonding orbital. We can connect them with these dotted lines. Okay, now each of the atomic orbitals is going to start with one electron. I like to show them as spin opposites so they can become spin paired. We're going to carry them down into the molecular orbital, starting with our bonding molecular orbital to put two electrons. Okay, this is the molecular orbital for molecular orbital diagram for the pi system only of ethene. This is what I want to do. We have one pi bond. We treat it just like the sigma bonds in He2 and H2 that we tried to use last time. It's just that the electrons are the pi electrons. So we have one pi electron here and one pi electron here. And that gives rise to our molecular orbital diagram. This appears to be the same as H2. Okay. Now, something else that kind of emerges from these types of simple patterns of highly complicated considerations for orbitals is that we can actually describe what the orbitals themselves are going to look like. So it turns out that when you draw the molecular orbital pi systems, you can consider them as a combination of overlapping or unoverlapping p orbitals. Let's look at what I mean. We can actually predict what the MOs look like. Okay? Now this takes into account the fact that we're using non-hybrid p orbitals, non-hybridized p orbitals in our pi systems. Okay? So we have a non-hybrid p orbital and another non-hybrid p orbital mixing together to make an anti-bonding MO and a bonding molecular orbital. Okay? To understand what these are looking like, and these are the two p orbitals, and by p orbital I mean the atomic orbitals, used to make the pi molecular orbitals. So there's something we have to be mindful of when we're trying to draw what the molecular orbitals actually look like, and that's the idea of an orbital node. This is a 0 point, a break, or a color flip. A 0 point, a break, or a color flip. Now, there is, and what these do, what nodes do, is they increase the energy of the orbitals. The more nodes in an orbital, the higher its energy. Okay, so the more nodes in an orbital, the higher its energy. Now let's look at what this looks like. If we look at the 1s orbital, the 1s orbital is just a sphere. But if we look at and let's just scratch the 1. Let's just write s. Okay, so if we look at an s orbital, its energy is 1, or its node number is 0. Nodes, again, are when we have color flips or breaks in the orbitals. A p orbital naturally has a node. Because we see a phase change as we go from the top lobe to the bottom lobe, and there's even a 0 point. Okay, we don't have this continuity of space throughout the entirety of the orbital. There's a break in the spacing, and that represents a node, a 0 point, or a node, slicing right through in between those two lobes. Now, the other thing to consider is that, this is true for all p orbitals. Kind of bisecting in the middle. Okay, so that is a node. Now, when we have a molecular orbital, excuse me, molecular orbitals can also have nodes. But what we do is we ignore the natural node from the p atomic orbital. Okay, so let me say that again. Molecular orbitals can also have nodes, can also have color breaks. And when we count the nodes, we just count them whenever we see a color break, but we ignore where the colors bisect in a typical p orbital. One thing before I touch on this and talk about where nodes are at in molecular orbitals is we could go back to the p orbital, and alternatively, we could have a phase shift from plus to minus. Whether or not we use pluses and minuses or shaded and unshaded reason is totally up to us. Pluses and minuses looks a little bit more mathematical, and all of these things are derived in mathematics, but the choice of which side is positive and negative is a little bit arbitrary because we could roll these things around in space if we needed to. The top side doesn't have to be positive. They're just different phases. They're opposite phases. So that's why I prefer shading, because it doesn't lock one side to being in plus or minus. They're just opposite of each other. Okay. So what we can do when we construct a molecular orbital is we can take two p orbitals and we can mix them together to make a bonding and an anti-bonding orbital. When we do the bonding orbital, we're going to have the lobe shadings kind of match up top to top and top to and bottom to bottom. So what we get is we get a bonding molecular orbital that looks like, I should draw that one curving in a little bit, where the shaded regions overlap with shaded regions and the unshaded regions overlap with unshaded regions. So there's a lot of overlap because there's in-phase interaction. Okay? So when the shades overlap, we see in-phase interaction, and that promotes bonding. Now, another way of looking at this is to depict this as a molecular orbital where I've got one C and another C, and they each contribute a p orbital. And instead of showing the distortion where they're kind of leaning into each other, I'm just going to show them where the shading matches up. These two things are the same, but the bottom one is easier to draw. So this is again taking two p orbitals and allowing for in-phase overlap to occur. We say that this bonding molecular orbital has 0 nodes. Now you might be like, well, isn't there a node slicing horizontally across that line where I've got the C's? Yes, but we don't count that one when we're looking at molecular orbitals, okay? We just prefer to say that the nodes start at 0, okay? So there's no nodes here. Now, what does it look like when we do have a node? Well, in that case, we would actually have out of phase interaction, where if our left lobe, our left p orbital has shaded lobe up, and right one has shaded lobe down, we're going to see out of phase overlap. And that's going to give us something that looks like this, where the orbitals are actually reaching away from each other because they don't have the opportunity to undergo in-phase overlap. This is an anti-bonding orbital. The orientation of the p orbitals that come together to form a molecular orbital is not productive for bonding because we don't have in-phase overlap of the atomic orbitals. And as a result, they're going to veer away from each other and not promote bonding. If we have to put electrons into this molecular orbital, we're not going to see a productive interaction of the two atoms, and a bond is not going to want to be formed. Now, another way of saying this is we have additional nodes. Okay, so nodes represent out of phase overlap. Not to get too quantum mechanic-y on here, But what we're showing with these orbitals is we're showing the solutions to wave functions that have been squared to give rise to three-dimensional shapes. And waves, which are described by wave functions, can add together in a constructive or an interfering manner. So when they add together, you get a bigger wave. But if they add where we've got tied up and tied down, this is kind of out of phase overlap or destructive interaction of the two waves, and you actually get something that's neutralized, right? If you take two waves that are moving in opposite directions and you add them together, you get something that's zero. Whereas if you take two waves that are in sync with each other, they get bigger, and that's in phase overlap. So that's what we're actually showing here with this in phase and out of phase overlap of these p orbitals, is we're showing the quantum mechanical kind of fruition of two waves interacting in a constructive or destructive interaction. And so we just show that more simply just by nodes. So an alternative and easier depiction for an antibonding orbital is if we just have our C atoms, we show the p orbitals that are provided by the pi bonding system. Again, all of this is for the pi bonding system. We just show the shaded regions moving in opposite direction. And we could put a dash line in here to represent we have a node. So we ignore the p orbital nodes that's slicing halfway through, and we only count the vertical nodes. Okay, so it turns out that each additional node increases the energy of the orbital. So each added node increases the energy of the orbital. So as you go to higher energy orbitals, you're usually going to see more nodes form. Now, what's cool about this is we can apply all of these rules to really complicated pi systems just by remembering a simple rule that as you increase the energy of a node, or excuse me, of an orbital, and it's a molecular orbital, the node count increases by 1. The node count increases by 1. That's super important for us understanding how to build molecular orbital energy diagrams, is to remember that our nodes always go up by 1. Okay, that allows us to look at more complicated molecular orbital diagrams like conjugated dienes. So molecular orbitals of, and it's not just dienes, it's conjugated pi systems. These apply the exact same rules. We just have more atoms and more electrons, and then resultingly, as a result, more molecular orbitals to consider in our molecular orbital diagram. Okay, so let's pick on this system. So we're looking at conjugated pi systems. So what we want to do is let's build the molecular orbital diagram for 1,3-butadiene, which is shown over to the left. Okay. To do that, what we need to do is figure out what's all involved in the pi system. So what's in the conjugated pi system? And from a previous lecture, we know that the conjugated pi system involves everything that is part of this double, single pattern within the molecule. Okay, that is to say, we have in the pi system 1, 2, 3, 4 atoms. Because all of those 4 atoms have a double bond or a single bond that's part of our double, single, double sequence. I should make note here that we stop at double bonds. So we don't go double, single, double, and then look for another single. It's only the double bonds that are involved because those are the only things that we can draw resonance structures to. So stop at the double bonds. Okay, so we have 4 atoms and we have 2 pi bonds. Why do we have 2 pi bonds? Well, we have 2 double bonds. Each of those double bonds has a sigma bond, which we ignore. We don't care about those right now. We care only about pi bonds in our pi system that has conjugation. So we have 2 pi bonds. It's the second bond in each of those double bonds that we want to consider. How many electrons? Well, the electrons we want to count are the electrons that are part of the pi system, not part of the sigma system. So these are going to be part of those second bonds, those pi bonds in this pi system. There's going to be 4 electrons. 2 times 2 pi bonds. So we have 2 electrons in each of the second bonds, or each of the pi bonds, for 4 electrons total. That's going to tell us how many of the arrows we want to add up with. Okay. So we have 4 atoms. We have 2 pi bonds. We have 4 electrons total. The 4 atoms tell us that we have then 4 p orbitals to consider. Well, now it doesn't make a lot of sense for me to draw p orbitals on the left and right because it's going to be hard to keep them all together. So instead, what I want to do is recognize that if I have 4 p orbitals to consider, each molecular orbital, the molecular orbitals, is going to be comprised of 4 atomic p orbitals. Okay, so we're going to take 4 p orbitals to make a bunch of molecular orbitals. How many molecular orbitals? And the 4 p orbitals, think about it for a second. How many orbitals do we expect to get out? How many molecular orbitals if we start with 4 p orbitals? Well, the orbitals in equals the orbitals out. So the 4 p orbitals will result in 4 molecular orbitals. Of those 4 molecular orbitals, we'll have 2 that are bonding, and then for each bonding, we need to have an anti-bonding. So we can't just have 4 bonding orbitals. That's not what the math tells us. It says that 2 have to be below the neutral point, 2 have to be above the neutral point. If we had an odd number, we'd stick some in the middle as non-bonding electrons or non-bonding orbitals. So 2 bonding and 2 anti-bonding. So what does this look like now? Well, we're going to have 1, 2, 3, 4 molecular orbitals. So this is going to be MO1. Actually, I'm going to start lower energy. MO1, MO2, MO3, MO4. How many nodes are in each of these orbitals? Well, if you look at this, we went up in energy. And there's a reason why they're not like tied, why 1 and 2 aren't the same and 3 and 4 aren't the same. The other thing I want to do is cut this energy, the molecular orbital diagram, in half, and this is going to be my 0 energy line. Anything below the 0 energy line is bonding. Anything above the 0 energy line is anti-bonding. If you put things below the 0 energy line, that's saying the electrons would prefer to be in those molecular orbitals than if they were in p orbitals all by themselves. So we have 4 orbitals. because we mix 4 p orbitals together. Now, within these 4 orbitals, we can consider overall shading, where we have 4 p orbitals, right? Each of the 4 p orbitals mixed together, and they resulted in 4 molecular orbitals. Each of those molecular orbitals actually can be kind of considered as 4 p orbitals interacting with some in phase or out of phase overlap. What I want to make note of is the node count. Well, it turns out, and this is one of these rules I said to highlight earlier, you actually increment by 1 starting with 0. So we know that we have 0 nodes. How do I know that? I haven't sketched anything in yet. I just know the rules of quantum mechanics say the lowest energy molecular orbital has 0 nodes. The next one 1, the next one 2, the next one 3. That's critical to helping us understand how we're going to see these things get shaded. So I'm going to go ahead and draw the 4 p orbitals. Oh boy, I ran out of space. I did a bad job in that. Wait, why am I adding 6? In my mind, I'm like thinking, should we do hexatrine? Anyway, sorry. Okay, so I added 4 unhybridized p orbitals. I haven't shaded anything yet because I got to make sure I have my nodes right. Well, it's just going to increase by increments of 1, starting with 0, 0, 1, 2, and 3. Okay. So what we can do is actually start shading these so that they have the appropriate number of nodes. If we look at the lowest energy molecular orbital, that's the easiest one because we have 0 nodes. To do 0 nodes, the shading matches along the top and the bottom. You could put the shading on top or the shading on bottom. It doesn't matter, but that's arbitrary, just as long as they all match. Now for nodes equal 1, we're going to split the molecular orbital in half and put a node here. What that means is I'm going to choose to put shading on top and then switch to shading down below. Now I have some in-phase overlap, but then I flip to the opposite side. You could have flipped your shading as being shading on bottom and then going to top if you wanted to. Now the last one, I'm going to skip 2 for a second. The last one is going to have 3 nodes, and that's where we have a color switch at each of the atomic orbitals that make up our molecular orbitals. So we go from color to no color to color to no color. And we could flip which one was on top or bottom. That's up to you. So we have 3 nodes along for the top one, and it's just a separation between each of the orbitals. When we had 1 node, we cut the molecular orbital in half, and that's kind of what we want to do here. So there's a few ways that you could introduce 2 nodes for the 3rd molecular orbital. But the way the math churns out is that we're going to split this in half so that we maintain symmetry, and that is by cutting right away, but then in the middle having some in-phase overlap before going to the outside. Now, when we label these orbitals are called pi 1, pi 2, pi 3, and pi 4. Sometimes psi 1, psi 2, psi 3, and psi 4, because for quantum mechanics, and those describe wave functions. So these are our labels for the molecular orbitals. Whew, we're done, right? Not quite. I'm going to switch up the ink so you can see this. The last thing we have to do is add the electrons, right? We're constructing all of these orbitals so that we know where the electrons exist so that we can determine the bond order. Okay, so I'm just going to switch up to blue. I'm drawing a little line right here to show where my electrons are going to go. So how many electrons do we have in this pi system? Well, if you recall from earlier, it's 4. We get 4 electrons, 1 from each of the bonds, so we have to fill those up. I'm going to start 1, 2, 3, 4. Starting from the bottom, add 2 before I move up to the next one. So from this diagram, we can see that 2 electrons went into pi 1. That was my molecular orbital with 0 nodes. 2 electrons, I shouldn't say went into, I should better as occupy pi 2. And what's great about these is that pi 1 and pi 2 are bonding orbitals. And so if we're only occupying bonding orbitals, we would say that this tells us that our pi system is stable and involves 4 atoms. Okay, so that's different than if we had 2 alkenes far away. These would just be 2 ethene pi molecular orbital systems separate from each other. 2 molecular orbital diagrams like the one we started with only a bonding and an anti-bonding, and then 1 node in the anti-bonding. Okay, those would be completely separate, but because we're in conjugation and we can involve these atoms by resonance, we take into account all 4 of them. The electrons get distributed. The 4 electrons get distributed across the 4 atoms through resonance or through these molecular orbitals. A molecular orbital that encompasses 4 atoms. What does that look like? Like, I can get what a molecular orbital, connecting 2 H's together. It's like 2 spheres come together to make a blob. But what about a molecular orbital that connects 4 atoms together? I mean, I guess there's like a blob that extends across all 4, but that's just 1 orbital. 1 orbital can hold 2 electrons. Well, what you just described, a blob across all 4 elements, that is pi 1 in this shading diagram. So I show here still pi 1. There's a blob on top and a blob underneath that encompass all of the atoms. We can also fit another orbital in there, one where there's a blob connecting across 2 and a blob connecting across another 2. That's pi 2. That's where we put the other 2 electrons. So we have space for all 4 electrons across these 2 atoms. And the way to think about what they look like is to consider the shading regime. Now, that's not the only reason why we do the work with all the shading in understanding the nodes, because you could just argue, well, just give me 4 lines and put some electrons in the lowest 2. Well, the reason why we're going to do the shading will come into when we look at how these orbital diagrams can be used to understand chemistry and chemical reactivity, not just the stability of molecules. And so that's what we'll look at next time. That's called frontier molecular orbital theory. Okay, so that'll do it for this time. So I'll see you next time.